Hello and welcome back to Unit 4. In Part 2, we're going to focus on forces and types of forces. So first off, we're going to take forces and divide them into two different types. Contact forces involve anything that is touching your object. So for example, if you have a string or a rope pulling on your object, that would be a force called tension. Any contact force between two surfaces. It could be a push or it could be a pull. For example, if you're sitting in a chair, the force between you and the chair would be this sort of contact force. This is known as a normal force. And it's not a normal force in that it's a regular, ordinary force. It's a normal force in terms of the mathematical use of normal. Normal forces always act perpendicular to the surface of contact. Remember, in math, a normal to a surface is a perpendicular to the surface. The last type of contact force is friction, and it always acts in the opposite direction of motion. There are a variety of non-contact forces. Gravity occurs between any two objects pulling toward each other. This one is more typically known as weight. You have the electric force, which occurs between charged objects interacting with each other, or it could be a charged object and a neutral object. You have the magnetic force, which is a magnetic interaction of two objects. The classic magnet pulling on the paperclip is a good example of that one. There are also two more in what is commonly known as, or commonly part of the electroweak theory of physics. The weak force governs radioactivity and is an internuclear force. The strong force is the one that binds the atomic nuclei together to keep all those protons from impelling away from each other. These last two, we are not going to be working with much in either this course or in the next semester, but I think it is good for you to know that these two forces exist. When I work with forces, I like to label my forces. Okay, I use two subscripts. The first subscript describes what is causing the force, and the second subscript is what it is acting on. So the force by object A acting on object B would be force FAB, or the force by object B acting on object A would be FBA. Okay. There are a variety of reasons that I like my subscripts. One, when I look at a particular object, that second subscript, the one that the force is acting on, all has to refer to that same object. Otherwise, it doesn't belong. If you can't identify the first subscript, then chances are it's a force that you really want to be on the object and just isn't there. It does not exist. When we get to Newton's third law, the subscripts are also good for identifying third law force pairs. So lots of uses for the subscripts. I do not require that you use them. You will see me use them. Okay. We also have labels that we use for our common types of forces. So N for normal force. Now you have to be a little bit careful with this one because you can get equations that look like this. N equals 5N. So the normal force on the object equals 5 newtons. So the two N's don't have the same meaning. And you have to pull that out of context. If you want to somehow distinguish your N's, maybe put little caps on them or something so that you know which one's the force and which one's the unit, again, that is perfectly acceptable. Typically, I use a lowercase f for friction because an uppercase F is kind of a generic force that doesn't fall into these particular four types. I use W for weight. Remember, weight is the force due to gravity. You're like, okay, well, why not use big G? Well, Big G is a constant that is used for another force later on. Therefore, W for weight works. Okay. And capital T for tension, because typically little t would be a time. Okay. Okay. So now we have weight. Weight is the force due to gravity on that stuff. But we also have mass. Mass is the amount of stuff that makes up something. The combined collection of protons and neutrons and electrons that make up that thing. Okay. These two quantities are very, very related. But if I take an object and move it from Earth to space, to the moon, and maybe then send it out of the solar system, the mass of that object isn't going to change. The number of protons, neutrons, and electrons that go into it are not going to change, or at least is not going to change in a way that can't be accounted for. So maybe something is being exhausted in terms of fuel. What I can keep track of how much fuel I've expelled and account for that. The object's weight, however, when I move it from place to place to place to place, that does change because that force, that weight, is dependent upon the gravity in wherever you are. You can calculate the weight by taking the mass and multiplying by the acceleration due to gravity for wherever you are. So on Earth, G is 9.8 meters per second squared. On the other hand, if I go to the moon, the acceleration due to gravity is about 1/6 what it is on the Earth. Therefore, G changes and the weight changes. When you plug into G here, this is a magnitude. Okay, so that G would be an unsigned number. I don't want to call it a positive number. It's an unsigned number, if you will. Okay, the negative sign will be put in elsewhere in the problem to indicate downward, assuming that downward is the negative direction. Okay. Friction resists motion and always points in the direction opposite of the velocity or opposite the direction the velocity would be in. So for example, if I have a ramp, nice rough ramp with a block sitting on it, at rest, without friction, the block would slide down the ramp. With friction, the friction points up the ramp. It's opposite the direction the velocity would be in. Okay. Friction comes in a variety of forms. Air resistance is a type of friction. The friction between the block and a ramp, that's a surface friction. Lots of forms for friction. Lastly, another one you might see is the force due to a spring. This is governed by a formula known as Hooke's law. And what Hooke's law says is that F due to the spring equals negative Kx. Okay. Well, X here is going to be the amount the spring is stretched or compressed. Okay. So it's how far you've moved this spring from its equilibrium position. K is what is known as the spring constant. Okay. This is a constant that changes from spring to spring. It is not a constant like, say, the speed of light, which is the same everywhere throughout the universe as far as we know. Okay, it varies from spring to spring. This negative sign, remember in physics, negative signs give you directions. So what this is telling me is that if I pull and stretch the spring, then the force is going to be trying to bring it back to equilibrium. It's going to try to compress it. So the force acts in the direction opposite of what the spring is stretched or compressed. Okay. This concludes part 2 of Unit 4.